Hello, in this video we'll establish a connection between two devices using the Controller Area Network, or CAN for short. In part 1, we'll set up an RA6M4 to transmit data. Then in part 2, we will configure an RA6M5 to receive the data and echo it back. In the CAN architecture, a microcontroller is paired with a CAN controller and connected to a CAN bus via the CAN transceiver. Initially, data moves between the CAN controller and transceiver before being transmitted onto the CAN bus. This setup enables nodes to communicate with each other independently via a shared bus, allowing for the addition or removal of nodes without disrupting other connected devices. In our project's hardware setup, a basic transceiver module is linked to the EK boards using the CTX and CRX pins. Additionally, a 120 ohm resistor between CAN-L and CAN-H serves as termination as per the CAN protocol. A second unit based on EK RA6M5 will be added as the second node in the network. Data will be exchanged between these two EK boards. So let's set up the first node with the EK RA6M4 board. We begin by launching a new C++ project in E-Square Studio. As usual, we will choose the EK RA6M4 board. For the remaining configurations, we can stick with the defaults. After the project loads, we can proceed to configure the peripheral ports. For this job, we only care about sending messages via the CAN, so we need to find the CAN option in the connectivity menu. We will stick with channel 0, so no need to change much there. You might notice that the CRX and CTX pins don't have any pin numbers assigned to them. We will need to check the pins tab to understand why. When we look at the individual pins, we see that pin 202 is currently set up for SPI, but we are not using SPI, so we can turn that off. This will give us some pins to use for CAN instead. Returning to the CAN configuration, we now notice that pin 202 and pin 203 are available for CAN communications. After assigning them, we will see them reflected in the configuration properties of the CAN stack. We can generate the project contents and start coding from the hull-entry.c file. We can enable a better view by selecting the C++ perspective. First, we will declare two CAN frame variables to store the transmission and reception data. The CAN frame data type is a custom structure defined in the r_can API file. It includes details such as the CAN ID and the type of CAN data, along with the data itself. This header file is accessed through the hull data header file and is automatically included when we added the stack. In the following section, we will introduce some flag variables to track the data transfer status throughout various stages of the program. Specifically, we will include two flags for reception and transmission and one for errors. Additionally, we will add a variable to store the reception ID. Three more variables will be included for program usage, one to keep track of the number of transfers, and an error and success code to identify status of the API calls. We also need to set some constants for our CAN data exchange. Mailbox 4 will be used for receiving frames and mailbox 31 for sending them. The address for receiving mailbox will be configured in the receiving array unit, and it would have to be 4. Lastly, we will define that our frame data length for transmission is 8 bytes. Next, we will create the callback function. This function will mainly run a switch statement based on event status. Our first concern is the reception complete status, activated when data is received by the CAN channel. We will assign the received data to the variables we set up earlier. The function's arguments are predefined by the FSP and are simple pointers, providing information about the frames in this case. Likewise, we will handle a transfer event. When this event occurs, we will set the transfer flag to true. We will also account for potential error events where the program will stop. Lastly, we will include a break statement as the default action in this switch case. With that, we conclude our switch statement and the callback function. Now, let's begin writing the hull entry function. First, we will declare a variable to hold any errors returned by the FSP API calls. Then, we will make the first API call to open the CAN channel. The arguments for this call are already specified. To ensure the function executes correctly and returns the expected status, we will use the assert macro. We are also going to set the received frame values to zeros. Next, we will set up a while loop. Before starting transmission, we need to input data for the transmit frame. We will fill in three fields: the frame ID, which is the destination frame address, the frame type, and the data length code. Using a for loop, we will populate the transfer data buffer. For each byte, we will add values based on the index of the data byte. This value will increment with each iteration of the while loop. Before performing the write operation, we will introduce a delay and set the transfer and receive flags to false. Then, we will call the CAN-write API. Its arguments include the transmission mailbox number and the transmission frame. In the next segment of code, we are implementing a conditional statement to manage the outcome of the write operation. The R variable is evaluated against FSP_success to check whether the operation was successful. If R equals to FSP success, signifying success, we increment the success_code variable to denote a successful operation and reset any previous error codes by assigning the error code value of 0. But if the return status R is not equal to FSP success, indicating an error has occurred, we set the error code variable to 99 to indicate the error condition and reset success code to 0. Then, the counter variable is incremented to maintain a count of all operations executed and add an offset to the next transmit data. Once the program has finished, we can build it and upload to our board using the debug function. We can utilize the expressions tab to monitor the status variables. We will add a breakpoint to the write statement at this stage to monitor the output right after its execution. We notice that the success code has been incremented to 1, meaning a successful write operation. The counter has also been incremented. In the next part of the video, we shall configure an RA6M5 as a second node which receives this data and echoes back. So, see you in the next video.